Good morning, everyone. Am I audible?
Yes, sir.
Yes, sir.
Okay. Soumya, can you please start the recording?
Yes, sir.
Okay. Okay. So this is your course that is Thermomechanical Processing of Materials. So today is lecture number 1 and 2. That is basically of Introduction to Thermomechanical Processing of Materials. Okay. Let me correct it. Introduction to. Okay. So you people have already gone through a few subjects that is on mechanical processing, obviously in earlier semesters, and also you have gone through heat treatment. That subject was taken by me only, I remember. So you have a good knowledge on this mechanical working, heat treatment, uh, and you also have gone through the top subject that is physical metallurgy, right? Introduction to physical metallurgy. Also, we have gone through the subject, I think, deformation behavior of materials. So I mean to say is you have a good knowledge on this mechanical processing and physical metallurgy part, basically. Fine. So this particular course will be completely linked with those earlier courses. Fine. So today's menus are like this. First is the main root of metal alloy processing and flow sheet. So uh, in this content, I'll be showing you what is the main root of processing of materials. Okay, what is mechanical processing and types of forces and type of processes. These are these are completely elementary things. Huh? What is thermal processing, and what is thermomechanical processing, and finally why thermomechanical processing. So that means today's lecture will be completely concerned with the elementary things. And finally, I will close the today's class by telling you why we need thermomechanical processing, or what is our main objective of this particular course. So main root of metal or alloy processing. We know that we don't deal with metals basically. We deal with alloys. So we'll talk about alloys basically. And here materials means, since we are metallurgists, so we basically focus on processing of thermomechanical processing of metallic materials, alloys. So basically, when we process any materials, basically they are basic two routes. We know that. One is the melting and casting route. One is the obviously powder metallurgy route. There are other routes sometimes like depositions and all. Fine, we can deposit the materials. We can process them by deposition and all. But the main route is the melting and casting route, where we melt the material first, or in other way we can say we produce the metals or alloys in molten state. That is by smelting, you know that. Or sometimes we collect scraps and we melt them. So first is the metal production by melting, then we do casting, and that kind of casting is actually continuous casting. Now that is not like batch casting, it is a continuous process. We are continuously pouring the molten liquid, and we are continuously drawing out the solidified materials or solidified alloys. Fine, in other end, right? So melting and continuous casting is the main metal processing route. And that means after casting we'll get a ingot, obviously. Solidified ingot. Huh. That solidified ingot will undergo mechanical processing, right? We process them by using forces, load, or by, you can say, stress also if you want, and we get a desired shape at the end with desired mechanical properties or desired properties. And we know that these are the main product of continuous casting, billet, gloom, and slab, and each component having particular applications. Some part will be used for making rods, coils, uh, something else, strips like that. Huh? Okay, so this is the flow sheet you can understand. So first is the molten alloy production, then it will undergo continuous casting, and continuous casting will give you ingots, bloom, billet, and slab. They have different dimensions and different purposes. And this solidified ingot. Okay, this is not moving. Okay, yeah. So this is the flow sheet, huh? So the solidified ingot uh, will give a mechanical working or thermomechanical working. Either you can say mechanical working or you can say thermomechanical working. We'll see the difference soon. Then we'll get final products with desired properties. So this is the simple flow sheet. Molten alloy production, it is undergoing continuous casting, then it is finally undergoing mechanical working or thermomechanical working, and you'll get final products. The final products, you understand, those are basically maybe coils, maybe strips, maybe rods, maybe bars, and those have particular uses. Now, different forces acting on workpiece during mechanical processing or metal forming or metal working. You see, we basically say metal working in metallurgy, basically. That is basically other people sometimes say metal forming because we are giving a particular shape or dimension to the ingots forming, or I can say mechanical processing. So these are the different forces acting on the workpiece during this mechanical working or mechanical processing, or thermomechanical processing. So these are direct compression. You know how compression is done. Hmm. And or we can have indirect compression. Hmm. So the difference between the direct and indirect compression is first, direct compressions means you can see the force acting on the workpiece is completely a compressive force. Fine. But in indirect compressions, uh, the workpiece will be given some other kind of force, maybe tension, but the at the contact point where the workpiece is in contact with the particular die, you can say, there the force will be in compression, but you are applying tension on the materials, right? So that is indirect compression, you can say. And simple tension will be there. You know how tensions, like simple tensile test, we know the direction of the tension, right? And shear also, you know, that is opposite direction. One end it will be in one direction, and the end it will be in another direction, right? And bending is very simple, you know that, right? So these are the different forces acting on the workpiece during mechanical working or mechanical processing or thermomechanical processing, you can say, right? Then different mechanical processing, metal forming, metal working processes. Okay, fine. You people also know these things: forging and rolling. Huh? These are the most common or most used process in industry: forging and rolling. Right. So here in forging, okay, I'll show you the images soon. Hmm. Then wire drawing, then extrusion, then deep drawing. Okay, then sheet formation by tension. So these are the different mechanical processing. Hmm. Okay, these are the images you can see. So you can see the first is the forging, right? So you can see this is one end of the machine, this is another end of the machine, this is your workpiece, this is this part is movable. This will compress the material. You can see the direction of the force. This is upward and this is downward. So this is a compression, and the workpiece will get a shape. There will be a reduction in the thickness, obviously, during the forging. Hmm. Similarly, this is rolling, right? We have two rolls. Okay, the moment of rolls will be in the same direction. Suppose like here, and this will be like in this direction. Okay, and this is your workpiece having a thickness of T0. When it will pass through the roller, in between the roller, you will get T1 thickness. There is a reduction in thickness again. And there will be elongation, obviously. So, and you can see this arrow mark showing you the compression. So these are the direct compression forces acting during the forging and rolling, right? And if you want to find out the true strain, true strain is epsilon naught. You can see that is logarithm T naught by T1 open L by V. So strain, this is true strain rate, huh? So this is true. This is the strain, and this is the total is the true strain rate. Huh? This L by B is the time, you can understand. Huh? This L by B is nothing but the time. Strain rate means strain upon time, right? So time is nothing but obviously length versus velocity, or distance versus velocity. So the length versus velocity. And strain we know that is basically uh, change in the dimension. Huh? Okay, then wire drawing, extrusion, and deep drawing. So you can see this is the image showing you. First image is the wire drawing, right? You can see this is your kind of die. This is your die, and this is your workpiece. The workpiece, and you can see we are applying a tension here. So this bigger thickness cylindrical specimen will come out as a smaller thickness or smaller diameter, right? And you can see this is an indirect compression, obviously, because the force acting here is compressive force, but we are applying a tension here. So that's why it is a indirect compression. At the contact point, the forces are compressive, but you are applying a tension. So it is a indirect compression. Fine. So extrusion, you can see this is also very, these are the dies. You can see upper die, lower dies, you can see. And this is a kind of plunger kind of thing. It will press, or ram, you can say. This will press the material through this particular space, and it will come out as a product in this direction. You can see at the contact point, you are applying a force like this. It is not a compression kind of thing exactly, completely. But here at the contact point, the forces are compression. Right? Then deep drawing. Deep drawing, you can see this is a particular die, and you put a sheet on it, and you press it, and it will come out. It will take the shape. Huh? So you can see again at the contact point, the forces are compressive. So this is an indirect compression method. Then other kind of mechanical processing or thermomechanical processing can say is tension, bending, and shear. You can see this is tension. You can see this is the die. This part is the die. You put a sheet on it, a horizontal sheet on it. Then you stretch it. You can see the direction of tension. This is a tension. The moment you stretch it, it will get stretched, and it is a kind of tension force. Then bending is very simple. You can see the shape of the die. This is the kind of die shape, and you are pressing at the middle part of the specimen. So the specimen was horizontal first. When you press it, it will bend. You can see the direction of force here again. Then this is shear. You can see from the top, it is from top to bottom direction. From the bottom, you can see from bottom to top direction is shear. So finally, these are all the mechanical working processes or metal forming processes. Forging, rolling, extrusion, deep drawing, and this bending, this tension, shear, right? Now processing of ingot. So we can also classify the this mechanical processing or this thermomechanical processing on the basis of, basically not thermomechanical processing, only mechanical processing on the basis of temperature. Temperature at which mechanical processing is carried out, basically. We can process the alloys at high temperature, we can process the alloy at room temperature, right? Or we can process the alloys at some intermediate temperature, right? So the processing may be two types, that is called hot working, and the one is called cold working. I'll show you the slide soon. But the main processes are rolling, as we know in industry. So I can write hot rolling and cold rolling, right? So you can see in hot rolling, basically we hot rolling, like the first steps in the hot rolling is called roughing operation, and final rolling part is called finishing operation. So first the ingot will come. Suppose a billet, you want to process a billet will come, and billet will undergo roughing operation. Then at the end it will undergo finishing operation. Right. So in the roughing operation, what happens? We apply high temperature to the material and we apply high strain rate. Right. But in the finishing operation, we apply basically like the temperature will be also low and the strain rate will be also low basically. We apply low temperature in the finishing operation because we want a good dimensional tolerance and we want a better surface finish. You know the problem with hot working or hot rolling, because during hot rolling and hot working, you understand the temperature is very high, so oxide formation will be there, so oxide scale formation will be there. So the problem is what? The surface finish will be poor, right? Anyways, then cold rolling. So in cold rolling it will undergo like lot of pair of rollers will be there simultaneously, and the hot rolled component will be passed through this kind of processing. And cold rolling means the processing will be carried out at a low temperature, comparatively very low temperature, or sometimes room temperature. It depends on the materials, which kind of materials you want to process. For example, if somebody will ask, like, you have an alloy of lead and tin, or you are processing only this lead and tin, then if you process them, if you mechanically process them at room temperature, it will be uh, it will be again hot rolling. It will be not cold rolling, because you understand the difference between hot and cold rolling is on the basis of recrystallization temperature. If you are mechanically processing the material above recrystallization temperature, it is hot rolling. But if you are processing the alloy below its recrystallization temperature, then it is cold rolling basically. So basically, this mechanical working processes are doing on the basis of their melting point. Because some people say, like, what is recrystallization temperature? It is basically zero point 0.5 TM. Hmm. TM is the melting point in Kelvin, right? And zero point 0.5 is the half of the melting point. So that means if you are processing the metals or alloys above half of the melting point, then it is hot working basically. But if you're processing the alloy below half of the melting point, then it is cold working, right? In this way, you can remember also. And some people say, like, hot working means the processing will be carried out at a temperature of zero point 0.5 to zero point 0.8 TM. And if it is a cold working, then the processing will be carried out at zero point 0.3 TM sometimes, or below zero point 0.3 TM. Some people say like that. And we know the advantage of cold rolling, right? You will get a better surface finish and you will get a significant amount of strength in the material. Fine. Okay. So now this is a comparison between hot and cold working. You people already know these things because you are going to appear your gate examination. You have a good knowledge on this. I know that, but still we'll discuss quickly about this. So hot and cold working, the difference. So already I've told you, if working will be above recrystallization temperature, that is hot working. If working will be done below the recrystallization temperature, that is cold working, right? That is the difference. Then if you look at the orientations of the grain, right? So if you match the grain orientation of the starting material, like ingot, and you match the grain structure of the product which is obtained by after rolling, you will see hot rolling basically. You will see they have a same structure basically. So that means the orientation of the grain will be random before and after. That means you will get equiax grain. Suppose your ingot, suppose your billet is having a equiax grain, you hot rolled it, you will again, after hot rolling, you will get again equiax grain kind of thing, right? And you understand, if the grain will be equiax, that means the property will be isotropic. The property will be same everywhere, or in every direction the property will be remaining same. If you want to measure the bulk modulus, it will remain same, right? Anything you want to measure, they will remain basically same in all crystallographic directions. That is called isotropic nature. Fine. But in case of cold working, if you roll it, if your initial grain structure is equiax and you roll it, below recrystallization temperature, you will end up with elongated grain, right? So you will not get, that means the grain will have now preferred orientations. Equiax grain means the grain have random orientations, right? And preferred orientations means the grain will elongate in a particular crystallographic directions, right? So obviously the property will be anisotropic in nature, right? If you measure the property in all crystallographic direction, it will be different. For example, if you want to measure the bulk modulus, it will be different in different crystallographic directions, right? And you people understand why this happens basically. Obviously, because in hot working, the temperature is available, then recovery, recrystallization will take place. But in cold rolling, you have a low temperature and it is carried out below the recrystallization temperature, so there will be no recrystallization basically. So obviously, the grain will remain elongated, it will not become equiaxed. Hmm. Okay, anyways, then if you measure the strength after hot working, the strength will not increase significantly. If you measure the strength, it will not increase significantly after hot working because of recovery and recrystallization, you understand? Because recovery and recrystallization will decrease the strength, hmm, basically. Hmm. And in cold working, you will get a sufficient strength or you will get a significant amount of strength in the material, right? So basically in industries, that's why the ingot are fast processed by hot working, then it will undergo cold working because the final material is the cold worked materials. We need a sufficient strength in that, right? Anyways, uh, then and the other differences are there is an increase in ductility in hot work materials basically compared to cast structures. Mhm. But in cold work, there is a decrease in ductility. Obviously, ductility is just opposite to that of strength. You know that, so that's why ductility will decrease here. Then electrical conductivity in after hot working, electrical conductivity is good, but here in cold working, the electrical conductivity is poor. And this again depends upon the presence of lot of dislocations, right? Lot of dislocations and lot of substructures, fine. And obviously in hot working high load is involved, but in cold working low load is involved. Huh. Then if you measure the residual stresses after hot working, you'll get a low residual stresses, but after cold working you'll get a lot of residual stresses inside your material. Huh. So these are the basic difference between hot and cold working. Then thermal processing. Okay, fine. So that means up to this we have talked about. That means I discussed about those mechanical working processes, huh? Right? And some parts are thermomechanical processing also, because if heat is involved, that is thermomechanical processing. Basically, you can understand. Then, but that heat should be sufficient. The temperature should be sufficient while mechanical processing. Okay, anyways, then thermal processing. So thermal processing is, you understand, that is basically we are talking about heat treatment. Already you have gone through that course, heat treatment. You know what are the objective of heat treatment. If you want to recall, we can recall like we can modify the grain structure, we can modify the properties, like we can modify the ductility, strength, toughness, right? We can modify the grain structures, means if you want coarser grain we can get a coarser grain, if you want a finer grain we can get a finer grain. And we can modify the phases, if you remember, or you can say we can modify the microstructures, right? We can modify the structure from perlite to martensite, from perlite to benite, from sometimes from austenite to ferrite, or austenite to perlite, right? We can modify the phases by doing heat treatment, you remember, right? And we can also remove these residual stresses, you understand. If you want, we can remove the residual stresses by doing heat treatment. A lot of things, we can modify the conductivity, we can modify the magnetic property sometimes. So a lot of things can be done by doing simple heat treatments. So that is, we can say, thermal processing. The material will be taken to a high temperature, like austenitizing temperature, then it will cool at a desirable rate. So basically, at the end, I can say thermal processing means high temperature heating will be done, and different cooling rates are involved. Huh. And you understand, sometimes like such as heating to the austenitizing temperature. So the austenitizing temperature may be AR1, AR3, and TR, and quenching will be done. Okay, let me ask. I'll stop here. Let me ask a question to you people. What is AR1? What is AR3? And what is TR? Can you people answer this? What is this AR1 temperature, AR3, and TR? Anybody can answer.
Hello, sir.
Soumya, can you answer? What is AR1? Okay. Hmm.
Sir, that is AR1 AC1 temperature.
AR1 is
AC1 temperature means a
A31
critical
temperature. Sorry.
temperature.
Sorry.
Sir,
Can you repeat?
critical temperature.
Critical temperatures.
Sir,
Okay,
these are
okay,
the
fine.
yes, sir.
Which one are critical temperature? TR is critical temperature.
No, sir. AR1, AR3.
Or critical temperature. Very good. Critical temperature means
Yes,
the
sir.
temperature at which phase transformation happens. Okay, very good. But what is the difference between
A,
AR1 and AR3?
sir, in Hypo Eutector steel,
Mm-hmm.
sir, the AR1 temperature is Eutector critical temperature and Hypo Eutector steel AR3.
No, no. Okay. Okay, you have tried at least.
Oxidation temperature.
Anyways, anybody want to speak anything? Amrita, can you answer this one? What is AR1 and AR3? Okay, Swastik, can you answer this one? What is AR1 and AR3?
No, sir. Sorry, sir.
You people are going to appear your gate examination on this Sunday, and you don't know what is AR1 and AR3. This is completely terrible. Okay, anyways, I don't want to waste time. Anyways, AR1 and AR3. See, here R is there. We can write AR1 or AC1, basically, right? Or sometimes we write AE1. Similarly, we can write AR3 or AC3 or AE3. Right? What are these? Yeah, in physical metallurgy and in heat treatment class, I already told you what is E, what is R, what is C. Right? C for chow phase, E for equilibrium, and R for that is the term I don't remember exactly. Royd instrument something. I'm not sure about that. I don't remember. But anyways, E means equilibrium, right? C means chow phase. Chow phase means when you are heating the materials, we use term C. But when we are cooling the materials from the austenitizing temperature, we use R. Right? So AR1 is the lower critical temperature. AR3 is the upper critical temperature. Right? So AR1 is the lower critical temperature. Right? So you are cooling the material from the austenitizing temperature, you can write AR1. Right? If you cool that material below AR1, then that means initial structure will be completely transformed into the new structure completely, right? Suppose you are, as Soumya is telling, you have a, suppose you have a hypoeutectoid steel, right? So that means above AR1, what kind of phase will be there? You have austenite plus ferrite, right? But below AR1, you have only, suppose you have only maybe your austenite will transform into ferrite and you have only ferrite. Let it be, right? Or if we are talking about, you may have perlite and ferrite both. Okay, that austenite may transform into ferrite, or that austenite may transform into perlite, and the ferrite will remain as ferrite. Okay, so above, if you are going above AR1, then you initial structure you have, suppose perlite, then the perlite will transform into your obviously ferrite and austenite. Okay, anyways, AR3 is the upper critical temperature. That means above that temperature you have only complete austenite phase, right? Or if you are cooling the steel from you are going below AR3, then you will get your austenite will transform into, suppose ferrite and you have ferrite and austenite both. Okay, so AR3 is the upper critical temperature, A1 is the lower critical temperature, TR is the, what is TR? TR is the recrystallization temperature. You have to remember. If you're going above recrystallization temperature, that means recrystallization will start. Okay, anybody remember what is recrystallization?
Sir, formation of strain-free grains.
Okay, very good.
Yes,
Formation
sir.
of
At which
strain-free
temperature
grains.
new strain-free grain are created.
Okay, very good. New strain-free grains are formed. Very good. That means if you have deformed the metals plastically at a lower temperature, then the material will accommodate lot of strain in it, right? A lot of strain energy will be stored in the material, right? And you have lot of dislocations, lot of defects will be there in the material, right? But the moment you will take the deformed material to a high temperature, that is above recrystallization temperature, then what will happen? Recovery and recrystallization will take place. Obviously, the defects will go away, they will get annihilated, and formation of new grains will take place along the high energy regions, like on the dislocations, on the grain boundaries, right? At the end, your grain become equiaxed, basically. Elongated grain will become equiaxed, that is recrystallization. Okay, anyways, then you understand. Okay, so then, and quenching to the steel in flowing water, rapid cooling from austenitizing temperature. So you understand, if you cool it, if you cool the steel at a very faster rate from the austenitizing temperature, then you will end up with martensitic structure, basically, right? So this is thermal processing. So you understand the conclusion of this thermal processing. You can modify the phases by doing thermal processing, and you can get desired properties. So now we are going to finish the topic here. So you can see, that means thermomechanical processing. Processing means you understand. Now thermo and mechanical, that means in thermomechanical processing, high temperature will be involved. That means, in other way, I can say heating and cooling will be involved. Obviously, holding part will be there, and mechanical means mechanical forces will be acting on the materials. So that means simultaneously heat will be involved and mechanical working will be involved in thermomechanical processing. Fine. So okay, before moving into the main topic, what is the objective of thermomechanical processing, we should see the cast structure. Suppose this is a cast structure. Can anybody tell me what are these?
Columnar grain.
Columnar grains, very good. But these are not exact, these are columnar, but these are dendrites. It is okay, you can see these are dendrites actually.
Yes, sir.
Yes,
So
sir.
these bottom part is showing you columnar dendrites, you can say, or directional dendrites, I can say, because these dendrites have a particular orientations from bottom to top, you can say, in this image. And these are actually equiaxed dendrites. Dendrites are there, but they are equiaxed. Equiaxed means random orientations. These dendrites have random orientations, but these dendrites are directional, the bottom part, right? So that means after doing casting of an alloy, you will end up with dendritic structure. That is one of the conclusion you have to remember. After doing continuous casting or after doing casting of an alloy, you will end up with dendritic structure. Some dendrites may be equiaxed, some dendrite may be directional. Okay, fine. Okay, I will show you a image again. Can you tell me what are these?
Sir, dendrites.
These are dendrites. Yes, very good. Actually, this is a real structure. This is the microstructure of a real ingot, but this is just a modeling part. Fine. So you can see these dendrites are directional, right? The first point is, what is the problem with dendrites? Dendrites are directional in nature, basically. You can see the direction is here from left to right. And if you remember, dendrites are tree-like structure. Dendrites are tree-like structures. So as a tree have lot of branches, they have primary branches, secondary branches, tertiary branches. So dendrites have also same primary branch, secondary and tertiary, you can see. So you can see the examples I can show you. This is, suppose I am talking about this middle dendrite. So this is your primary. This part is the primary. Secondary ones are, these one are secondaries, right? perpendicular to primary, huh? And tertiary are the small part, the small parts, the small branches here. You can see the small branches here are tertiary. So dendrites have primary dendritic arm, secondary dendritic arm, and tertiary dendritic arm. So these secondary dendrite will be always perpendicular to primary, and tertiary will be always perpendicular to this secondary arm, right? So this is one primary dendrite. This is one primary dendrite. This is one primary dendrite, and this two is showing you secondary dendrites. This is one secondary dendrite. This is one secondary dendritic arm, right? This is one secondary dendritic arm. But is tertiary? You can see these are the tertiary, small. Hmm. The tertiary dendrite. So the point is what? Now, what are the problems? So after doing casting, you are getting dendritic structure. So what are the main problem with the dendritic structure? That is the main question. Okay, you people have also gone through the casting subject. I know that. So can you tell me what is the main issue with dendrites? Which which cast structure is good? Equiax cast structure is good or dendritic cast structure is good? Let me see who can answer.
Request.
Equiax.
Equiax. Very good. Equiax is very good because equiax structure means it has random orientations. So the property is mechanical property you are going to get is fine. It is same everywhere, right? But if you are getting dendritic structure and that dendritic structure is also directional, the property will be not good because the dendrites are directional. You are saying you can see. Hmm. And other difference is dendrites are bigger size grains. You can say dendrites are coarser grains and we don't want coarser grain. Coarser grain is not good for the properties of the steel or properties of the any material or any alloy, right? So one issue is these are directional. Second issue is they are coarser in size. Coarser grains are not good. And other problems. Can you tell me any other problems with dendrites? Okay. Uh, w- w- what is the space between the dendrites? What is that called? The space between the dendrites are called what? Like this is the gap between the two dendrites, two primary dendrites, or you can say this is the space between two secondary dendritic arm, or you can see the space between tertiary dendritic arm. So what is that space called? That is called interdendritic region. The space between the dendrites are called interdendritic regions. And can you figure it out? What is the difference between this dendrite and interdendritic region? Just have a look. You'll get the thing. The check the interdendritic region and dendritic region. What is the difference you are seeing? It is written over here. Just check it. In interdendritic region, steel molten alloy is present. That is a liquid, and dendrite is nothing but it is a solid. It is okay. You people are getting my point. So tell me if this is the situation and what happens to the composition. If this is the situation, what happened to the composition? Do composition remain same everywhere or it will be different?
Sir, different.
Yes, different. So how it will be different? Where the composition will be changing?
Sir, the interdendritic region, the composition will vary.
Okay. Okay. In other word, I can say lot of solute will be rejected by these dendrites when they are growing. They are rejecting the solute. The solute will get rejected to the interdendritic region. So concentration of the solute will be more in the interdendritic region, right? So there is a variation in the concentration. If there is a variation in the concentration, the term is called what? Technically, we metallurgy people called it what? If there is a variation in composition occurs in a solidified material, that is called Okay, Shweta, can you answer? If there is a variation in concentration during solidification, the term is called what?
Yes, sir. Sorry, sir.
Okay, Pratiksha, I think Pratiksha can answer. Pratiksha, can you answer it? If there is a variation in concentration during solidification, that particular term is called what?
Sorry, sir.
That okay, anyways. The term is called segregation. Now you recall this term, segregation?
Yes, sir. Yes, sir.
Segregation means there is a change in composition from one location to another location in a solidified material, right? Because this segregation sometimes is due to rejection of solute. The solute will get rejected from the solidified particular. See, dendrite is forming means dendrite is growing in a particular orientation in a particular direction, right? All the things are not getting solidified at a time. So that means still some liquid is present, some solid is present. So solute will get rejected from the solid part. Hmm. To the liquid where liquid is still there. So obviously there will be a segregation. So another issue with this thing is the segregation problem. The concentration of solute is not same everywhere, right? So this is another issue with the this dendritic structure. So that means in the interdendritic region the concentration of solute will be higher. So obviously dendritic have low solute concentration, but interdendritic region have higher solute concentration. So it doesn't mean that the interdendritic region will not solidify. It will solidify later with more solute concentration. Okay. So these are the main issues. So finally what I mean to say, the main issue is the concentration of the solute or concentration of alloying element is not same everywhere after solidification, right? So obviously the property will not same everywhere. The property will be different. You have coarser structure, you have directional structure, your solute concentration is not same everywhere. The property will be different, right? And you have coarser structure as I told, right? And sometimes suppose there are certain alloying elements, those which form carbides, nitrides, or carbonitrides, those are basically precipitates. So what will happen then? Or sometimes there are certain alloying elements which form intermetallic precipitates. Then what happens? You'll end up with intermetallic phases or precipitates in the interdendritic region, right? So obviously, what will happen? The materials will be brittle. The solidified material or ingot will be brittle in nature because of these kind of things. So finally, the conclusion is what? If these are the main issues, then we cannot use a solidified ingot directly into our process because of these kind of limitations or these kind of disadvantages we have, right? So we need to remove all those things. We need to solve this issue before putting the material into application. We need to resolve these issues. Resolve this. We want to resolve this coarser structure. We want to resolve this directional structure. We want to resolve this in homogeneity or segregation problem. Right. We want to resolve these intermetallic phases present particularly in certain locations in the interdendritic regions. So to resolve this issue, we have to do thermomechanical processing. So now you people have understood why thermomechanical processing is essential, or what is the main objective of this thermomechanical processing. So now the question is why thermomechanical processing? So hence the first answer is break the cast structure of the ingot and to get homogeneous chemical composition. So this is the first point. We have to break the cast structure. As we have seen, after doing casting, continuous casting or casting, normal casting, we'll end up with dendritic structure. So we have to break these dendrites to get homogeneous chemical composition and to get equiaxed grain. Or in other way, we can get a small dendrite if you want, or basically equiaxed grain, right? So I can say after casting the molten liquid alloy, the structure obtained is dendritic one, that is tree-like, having multiple branches, primary, secondary, and tertiary branches. You have seen from the figure, right? These dendrites are bigger in size and directional too, as I told earlier, right? And moreover, there is an interdendritic region where the solute concentration is more, as this part solidify later during solidification, as I told, right? You have to remember this important line. The part which solidified later have more solute concentration, because solute is getting rejected from the solidified part to this molten liquid, right? So concentration of solute or distribution of solute is non-uniform, leading to inhomogeneity, as I told. Sometimes intermetallic are formed in the interdendritic region, which already I have talked about, which are brittle in nature. So this is one of the reasons why cast products are not used directly into application. So first of all, we have to break the cast structure. That can be break by doing thermomechanical processing. Okay. So property is non-uniform in the ingot. Due to this, so this kind of structure must be broken down into equivaxed structure and make the composition uniform. So can you tell me, anybody remember this equilibrium cooling and non-equilibrium cooling? If you are going, okay, fine. In industry, can you tell me, in industry, the cooling is equilibrium cooling or in equilibrium cooling? What kind of cooling is done in industry, basically? After getting the molten liquids, they do equilibrium cooling or non-equilibrium cooling? Can I get an answer from Amrut Pritam Mishra or Amiz?
Article. Hello, sir.
Yes, Amrut, can you answer in
Sir,
industry?
sir, now I have internship.
Okay, you can leave. If you have internship, you can leave.
Yes, sir. Yes.
Okay, Aditya, can you answer? Or Samrat can answer, I think. Samrat? Okay, Rutuparna, can you answer this? In industry, the cooling is equilibrium cooling or non-equilibrium cooling? Okay, anyways, basically in industry, we want to cool the liquids at a very fast rate because we want higher production rate. So cooling will be obviously non-equilibrium cooling kind of thing, right? So if you do basically non-equilibrium cooling, you will end up with this kind of structure. Sometimes. Inhomogeneous sometimes. Sometimes, since the
Sir, we
cooling
can say
is,
continuous cooling.
yeah, that is continuous cooling, but I am talking about equilibrium and non-equilibrium cooling. You already have gone through that part in IPM, I remember, right?
Yes, sir.
Equilibrium cooling means you are cooling the sample at a very slow rate, so you'll get a homogeneous chemical composition, because cooling rate is so slow that there will be a diffusion and composition will be uniform. But if you're going for non-equilibrium cooling, sometimes you may end up with inhomogeneous compositions, right? Anyways, we will not discuss that right now, but anyway, so you understand, to break the cast, we have to break the cast structure. That can be done by this thermomechanical processing, right? What can be done? You take the ingot, you put the ingot to a high, inside the furnace at a very high temperature, like suppose 1200 degrees centigrade for sufficient time. The composition will be uniform. Then you forge it, for example, or you roll it. The cast structure will be broken down and it will become equivaxed. Okay,
Yes,
because
sir.
high temperature
Gaurav sir
brings,
link.
sorry.
Sir, Gaurav sir link पठाले next class में.
Okay, you can wait for 5 minutes. I'll finish it.
Okay, sir.
Then another issue with the cast structure is you have porosity and cavities. You have already gone through that casting defects, right? You have blowholes, surface holes, porosities, right? So those defects also can be removed by doing thermomechanical processing, right? If you are doing forging, hot forging, then those pores or porosity will be getting closed, right? So the problem will be solved, because if you have porosity and you are putting it into application, then your crack formation will start from the porosity part, because that is a discontinuity, and the concentration of stress is always higher along the discontinuity part. So those pores and cavity must be completely closed by doing this thermomechanical processing. Okay. Then refine the microstructure. Already I have told you this cast structure are basically coarser. So coarser structure are not good. The coarser grain structure are not good basically. So by doing thermomechanical processing, we can get again EQX grain with small size. So grain refinement can be done, right? And you remember the Hall Page relationship. Sigma. What is the Hall Page relationship? Can you tell me quickly? Anybody? Sigma y is equal to sigma naught plus k d to the power minus half, right? Sigma y is the yield strength, right? So yield strength depends upon the diameter of the grain. If the grain diameter is small, your yield strength will be high. If the grain diameter will be bigger, yield strength will be low. So sigma y depends upon the d, right? Then finally, by thermomechanical processing, also we can get a crystallographic structure in the cast structure. Sometimes crystallographic structure are also good in our material. Texture means a preferred orientations. Sometimes we want a preferred orientation in our cast structure. That can be done also to get certain properties. Suppose we want high. Suppose we want high permeability, magnetic permeability in certain directions. So we can orient the grains in that particular direction to get high permeability. Suppose we don't want high permeability, we can also orient the grain in that directions also, right? Certain properties can be get in a preferred orientations, right? So we can obtain preferred orientations by doing this kind of mechanical processing or thermomechanical processing. Okay. So I will end this topic. You can see step are as follows in processing: edge cast structure, then high temperature homogenization, then thermomechanical processing. Okay. Okay, I'll end this meeting here. You please, Soumya, you take the attendance. Huh?
Yes, sir. Yes.
Take the screenshot and send me the absent list. And you ask your friend to stop the meeting. Huh? And you ask your friend to send me the video through mail. Okay. Okay,
Okay,
you
sir.
people can leave right now.